All right, so we've been talking about how to make two triangles congruent. We have a lot of options, whether it be side, 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 angle, side, angle, 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 side, or hypotenuse, leg. Don't forget about right triangles. We have that shorter guy there, okay? Well, let me ask you this. What if we had triangle ABC and triangle XYZ, and I told you that AB and YZ were congruent, and I told you that angle B and angle Z were congruent, and I told you that segment BC and segment XZ were congruent. What would you know about those two triangles? Well, hopefully you're looking at that and saying, well, the two triangles are congruent, so I can say that triangle ABC is congruent to triangle, and you'd have to name the other one YZX to make sure that all the parts are corresponding, they're matching, right? Okay, so the two triangles are congruent, and we're going to use at side angle side to make that happen. Okay? Well, then let me ask you this. What would you know about angle A and angle Y? Automatically, what would you know? Well, since we have our congruence statement here, then hopefully you're looking at this and saying, well, angle A and angle Y would be congruent as well because they match. In our congruent statement, they match. In other words, they're corresponding parts. So, I mean, we didn't measure angle A and angle Y. We don't have a definition, a theorem, or a postulate that makes angle A and angle Y congruent. But we know they're going to be because A and Y are corresponding parts of two congruent triangles. And therefore, they have to be congruent. Okay, that's our next theorem, actually. It says that, so when we use the shortcuts to make two triangles congruent, we're leaving some parts out. We're not actually saying that some parts are congruent. But once we know that one whole triangle is congruent to another whole triangle, that all 6 parts are congruent. And so what the theorem says is that when one triangle is congruent to another, all 6 parts are automatically congruent. And that's because we know that corresponding parts of congruent triangles are congruent. And the way that we abbreviate that theorem is by just CPCTC. That's how you'll see it written. CPC stands for corresponding parts of congruent triangles are congruent. And that's where the abbreviation comes from. Okay? So sometimes it may be that we need to prove 2 triangles are congruent in order to make a set of corresponding parts congruent. Okay? For example, here we have this hang glider, right? And we want to make sure that all the parts in this hang glider are congruent. All the angles that are created when we put this thing together are the same, or at least pairs of angles. Certain angles are the same. Certain rods need to be the same length and all that kind of stuff. So as we're designing this out, we want to make sure that that's the case. Well, we don't necessarily have to measure out every last little thing in there. Because there are triangles involved in making a hang glider, we only have to worry about a few parts. Okay? So, for example, if these 2 triangles that are created by the hang glider, triangle QRT and triangle SRT, we need to make sure that all those parts are congruent. So how can we do that? Well, if we make sure that angle 1 and angle 2 are the same, and we make sure that angle RTQ and RTS are the same, then that should be enough. How? How is that possible? Okay? Well, if we make sure that those parts are congruent, then we're automatically going to know that the rest of the parts are, including QT and ST. Okay? So I think it's helpful to pull those 2 triangles out of that hang glider and rewrite them and mark the pictures so that we can kind of see what's going on. So angle 1 and angle 2 are congruent here. Oh. And angle RTQ and RTS are congruent. So how does that help us make QT and TS congruent? Well, if we can somehow, because QT and TS are sides of these two triangles, if we can somehow make them congruent, then we'll know that QT and TS are automatically congruent because they're corresponding parts. So how do we do that? Well, we already have RTQ and RTS. By reflexive, we would know that RT is congruent to itself. And so we have two parts so far. We need one more. We have to think back a while ago. We know that angle 1, to a theorem that we did a while ago, we know that angle 1 and angle 2 are congruent. We also see, and angle 1 and angle 2 are not in our triangle. So it's not really going to help us right now. But this angle and this angle are a linear pair. And this angle and this angle are a linear pair. So we had a theorem a while ago that said if two angles were supplements to two congruent angles, then they're going to be congruent. That's what's going on now. This angle here and this angle here are supplements to angle 1 and angle 2 because they form linear pairs with those guys, right? But if that's the case, then because of the congruent supplements theorem, we know that they themselves have to be congruent, right? So, and it is the theorem that we talked a lot about in a class period a while ago, but we haven't really revisited it since. Okay, but since that's the case, now I've got angle RQT and angle RST that are congruent. Now my two triangles are congruent. So triangle QRT is congruent to triangle SRT, and I'm going to use angle, side to do that. That's the way the picture's marked, right? Now, if that's the case, then QT and ST are going to be congruent because they are corresponding parts of two congruent triangles. And so by CPCTC, I know that those two parts are going to be congruent. Okay, that's a use for those corresponding parts. Okay. All right, try to use CPCTC in a proof in this guy. So stop the video, and then when you have your proof written out, start it up again and see how you did. Okay, so how'd you do? There's some given information in here, not up here, but from the picture. That given information were that AB and BC are congruent and AD and DC are congruent. So we can use that as our givens. Okay, great. Now, we're trying to prove angle A and angle C are congruent. One of the ways that we just learned that we can do that is if I can somehow make these two triangles congruent. And so that's our goal. We need to make sure that when we're writing a proof that we know what the goal is. Where are we trying to go? Right? When you leave your house, you don't just leave without a destination in mind. Otherwise, you're just sort of aimlessly wandering around. So you need to know where you're trying to go. I'm trying to make angle A and angle C congruent. And if I can make those two triangles congruent, then I know that they'll automatically be congruent. So that's sort of the idea here. All right, so that's our given information. I love it when two triangles share sides because I get a free congruent part by reflexive. So now BD is congruent to itself. Now all three sides of both triangles have been marked congruent, so the two triangles are going to be congruent because of side, side, side. Remember that your shortcuts, side, 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 side angle, side, all those guys, are methods for showing two triangles are congruent. You don't want to use that as a reason for making anything else congruent other than two triangles. Okay? Now, because those two triangles are congruent, angle A and angle C are going to be congruent because they are corresponding parts of congruent triangles and therefore are congruent. So that's how that proof would look if you're trying to make two parts congruent instead of two triangles. Okay? All right. A little bit more practical use for this idea of corresponding parts of congruent triangles being congruent. Okay? Let's say that we're building a bridge and we want to build a bridge across this river. Okay? Well, we need to know how wide the river is so I know how much material to use and how to go about bidding the project to try to win that project to build the bridge. Last thing I'm going to try to do is, have someone hold the end of the tape measure on one side of the river, jump in the river and swim across and try to measure with the tape measure. That's ridiculous, right? So what we can do is we can use the idea of corresponding parts. And here's how. So N and P, I'm going to put stakes in the ground at N and P. That's going to be where my bridge goes. Okay? Then what I'm going to do is I'm going to walk down. If I'm on this side of the river, I'm going to walk down and put a stake in at point K. And I'm going to do it so that NK and NP are perpendicular. And the reason why I'm going to make sure of that is because when NK and NP are perpendicular, I know I get a right angle. Okay? All right. Well, great. So now I have a right angle here. Then once I have NK in here, I'm going to place M so that's right in the middle of N and K. So that M is the midpoint of this segment NK. I know that if M is the midpoint of segment NK, then NM and KM are going to be congruent. Okay? Then what I'm going to do is from my stake at point K, I'm going to walk directly out to a place at point L. And I'm going to keep walking out until L, M, and P are all collinear. They're all on the same line. Okay? So I'm going to place that stake L strategically, just like I did the stake at point K. Okay? So that if I make L, M, and P collinear, then I'm going to end up making these two triangles, NMP and KML. Now, I'm also going to make sure that I stick the stake in the ground at L so that LK is perpendicular to NK. And again, I'm going to do that because perpendicular lines form 90-degree angles, and so I'm going to have a right angle here. Okay? Now, look at what happened. Right? I've got these two triangles now, and I've got midpoint creating these two congruent segments. I've got two right angles, N and K, that we know are going to be congruent because they're right angles. And then I'm also going to have these vertical angles that are congruent. Right? And because of angle, side, angle, I know that these two triangles are going to be congruent. So because of angle, side, angle, triangle, MNP is going to be congruent to triangle MKL. And that's by angle, side, angle. And because of that, I know that NP and KL are going to be congruent because of CP-CTC. They're corresponding parts of congruent triangles and therefore must be congruent. So what does that tell me, right? That tells me that if I find the distance from point K to point L, it will be the same as the distance from point N to point P. So now I can measure a distance on nice, safe, dry land and know that that distance is the exact same as the width of the river. And then I can go bid my project and hopefully start building that bridge. Okay? Surveying is a very big use of geometry. Okay? And that's one way. Okay, and that walks you through what we just talked about. Another quick proof, and it introduces another idea that we've long since forgotten. So try to write it out. Remember what bisect means, and that'll help. But try to write the proof out, stop the video, and then restart it again and see what you should have done. Okay, how'd you do? First things first, yx and wx are congruent because it was given, right? And it's been marked. Now, zx bisects angle yxw. That was given as well. What does that mean? If zx bisects angle yxw. Remember, bisect means cut in half. So we're taking that bigger angle, YXW, and we're cutting it in half. That means that this angle and this angle must be congruent. And the reason why is because of the angle bisector. It's the definition of an angle bisector. So those two angles are going to be congruent. Okay? Well, great. Oh, shoot, we stopped. We need to make sure that we understand where we're trying to go. I didn't do that again, right? I'm wandering around aimlessly, having no idea what I'm supposed to be trying to do. Well, we're trying to make YZ and WZ congruent. YZ is here, WZ is here. And there's a couple of different ways we can attain that goal, but one of them is to make some triangles congruent. Now, which triangles? Well, which triangles use YZ and WZ? This triangle uses that, and this triangle does. So I could try to make those two triangles congruent. But this triangle and this triangle does also. So I've got a couple of options here. Well, since I'm talking about this side and this side and this angle, then it's looking like I'm trying to make these bigger triangles congruent, not those smaller ones in the bottom. So that's our goal here. All right, so I'm going to keep going. I've got this side and those angles. And I'm trying to make those big triangles congruent. Well, the next statement, XZ, XZ, we know where that's coming from. I love it when two triangles share sides. We can use reflexive to say that that piece is congruent to itself. So I end up with this, this, and then this. And that's enough information to make those big triangles congruent by side, angle, side. And so that's going to be the reason for our statement number 5. And then because those two triangles are congruent, we see that YZ and WZ are corresponding parts. And so therefore, those guys are congruent because they're corresponding parts of congruent triangles, and therefore they are congruent. Or CPCTC works. Okay? And so it's the idea of this angle bisector that we haven't talked about for a while. But again, any definition, any postulate, or any theorem that we've talked about in the past, we can still use. So you need to remember those. All right? So there you go. That's corresponding parts. That's how we use congruent triangles. Okay? Now, a couple of words about isosceles and equilateral triangles. And there's a really neat way of walking through and discovering some of these theorems that if you ever want to sit down and try to do, let me know and I'll walk you through how to do that. Okay? But first things first, isosceles triangle. There are parts to an isosceles triangle. And here they are. We've talked about this before, but we'll do a quick refresher. The two congruent sides are called legs. Okay? The angle that's formed by the legs, or the angle that is in between our two congruent sides, is called the vertex angle. Okay? The third side, so the most of the time the side that's not the same as the other two, is called the base. And then quite cleverly, the angles that are next to the base are called base angles. Gee, wonder where that name came from. Okay? But those are your parts. You need to remember those parts so that we can use that terminology. Okay? All right. With those parts in mind, and through some discovery that we did in class, and again, I'd be more than happy to walk you through that some other time, here's what we know. We know that if, and it's called the base angles theorem, if two sides of a triangle are congruent, then the angles opposite them are congruent. In other words, in an isosceles triangle, if the legs are congruent, then the base angles are. The angles opposite them are congruent. Okay? So if we know that it's an isosceles triangle, then the base angles are going to be congruent. That's why it's called the base angles theorem. Okay? Well, there's also the converse, which is true. The converse says, okay, if two angles of a triangle are congruent, so here, if two angles of a triangle are congruent, then the sides opposite them are congruent. So go across, and those are going to be your congruent sides. Okay? And so that's automatically going to be true, either by using the base angles theorem where we know the sides are congruent, therefore the angles are, or if we're going to use the converse where we know the angles are congruent, therefore the opposite sides are. There's a difference there, and the difference is what information we know and when. Okay? So how do we use that? Well, in this picture here, what if we knew that HG and HK were congruent? Then which angles would you automatically know were congruent? Well, this is an isosceles triangle, and the base angles are going to be congruent. So go across, and we've got angle G is going to be congruent to, we can't call that angle K. We've got to call it angle GKH. There are too many angles at K. Okay? So that's one use. That's what we know from this, right? Now, it works the other way too, right? If angle KHJ is congruent to angle KJH, then the sides opposite are congruent. So just go straight across from those angles, and we've got side KJ, so segment KJ is going to be congruent to segment HK. Okay, we know that automatically from that base angle theorem and the converse. Okay? Now, as an extension to the base angles theorem, right? So the idea that opposite sides and angles, if two angles are the same, then the opposite sides are as well. In an equilateral triangle, all the sides are the same, right? So in an equilateral triangle, if all the sides are the same, then it makes sense that all of the opposite angles are going to be the same. Okay? It has a lot to do with this idea of, this idea of if I've got this angle here, right, and I connect it into a triangle. If I want to make this angle bigger, right? If I want to make that angle bigger, then I have to extend this out here. What has to happen to this opposite side? Well, this opposite side would have to get longer as well, right? So the bigger the angle in a triangle, the longer the opposite side. Well, if none of the angles, if none of this, and vice versa, the longer the side is, the bigger the opposite angle has to be. Well, in a triangle, if none of the sides are longer than the other one, right, all the sides are the same length, then their opposite angles are going to be the same. So an equilateral triangle is also equiangular, where all the angles are the same. And it works the other way too. Okay? If all the angles are the same, then none of the sides have to be longer than the other one. So all the opposite sides are the same. And so if a triangle is equiangular, then it's going to be equilateral. Okay? So basically, you have some congruent angles, go right across from those angles, and those sides are going to be the same as well. All right? So some uses for this. Okay? Find the measure of angle PQ and R in this triangle here. Well, the triangle is an equilateral triangle. All the sides are the same, so all the opposite angles are going to be the same. I don't know what any of these angles are, so I'm going to let them all be x, since they're all the same. I do know that the angles of a triangle have to add up to, you guessed it, 180. So we can write the equation like this. We get 3x equals 180. Now divide both sides by 3, and we see that x is 60. So in an equilateral triangle, which is also equiangular, all the angles are 60 degrees all the time. Equilateral triangle, angles are 60 all the time. Okay? Now, find the length of ST here. Find the length of ST here. Well, it's an equiangular triangle, therefore all the opposite sides are exactly the same. So if this guy is 5, that means ST is 5. Okay? Easy enough. Now, I've got one more thing I want to show you, and then we'll be done here. is I want to extend this to isosceles triangles too. So an algebraic use, this isosceles triangle thing, right? So what if I told you that this angle measure, the vertex angle of an isosceles triangle was 50 degrees, or even something that makes more sense, 70 degrees. And we'll call this ABC. I want to find, sorry, this is not going to be in your notes. I want to find the measure of angle A and the measure of angle C. Don't know what A is, so let it be X. But since this is an isosceles triangle, the base angles are going to be the same, so these base angles are going to be the same. So I'll let that base angle be X. Well, I'm still in a triangle, so I can add up all those angles and set them equal to 180. Now, combine like terms, subtract 70 from both sides, and 2x is equal to 110. Divide both sides by 2, and x is 55. So both those measures of those angles are going to be 55 degrees. Not because I found x, but because that's what angle A and angle C are represented by. So something else that you need to keep in mind too, the base angles, you can always let them be the same in an isosceles triangle since they're congruent. Okay? That's it. Homework's out in Canvas. Go check it out. We'll see you guys next time. Don't forget you have a quiz.